Hello and welcome to the 24 Hours of Past Summit Preview 2016. We're excited you could join us today for Kathy Kellenberger's session, Indexing for Beginners. This 24 Hours of Past event consists of 24 consecutive live webinars delivered by expert speakers from the PAST community. The sessions will be recorded and posted online after the event. To access any on-demand sessions, please visit www.24hoursofpast.com. That's www.24hoursofpast.com for all session links. My name is Jonathan Stewart, also known as SQLox, and I'll be your moderator today. I have a few introductory slides before I hand over the reins to Kathy. If you require any technical assistance, please type your question to the question pane located on the right side of your screen and someone will assist you. This question pane is also where you may ask any question throughout the presentation. Please feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions aloud to the speaker. You are able to zoom in on the presentation content by using the zoom button located on the top of the presentation window. Also, please note that there will be a short evaluation at the end of the session. Your feedback is extremely important to us, so please take a moment and complete it. It will appear in your web browser after the session. I'd like to also take a moment to thank our presenting sponsors, Microsoft, Idera, and Attunity. In addition, I'd also like to thank the supporting sponsors for this event, Hewlett-Packard Enterprise and SQL Sentry. The staging of 24 Hours of Past would not be possible without their generous support, and they are the reason why this event is available free of charge. So make sure you explore everything PAST has to offer for data professionals. You can join local user groups around the world, special interest groups, find free online resources throughout our Learning Center, and read up on the latest community news in the Connected newsletter. Next, I'd like to bring your attention to the upcoming PAST Summit. This takes place in Seattle, Washington this year from October the 25th through the 28th. PAST Summit 2016 will feature over 200 sessions with world-class data experts. It's the perfect place to network with experts and peers, and you can meet the engineering team behind SQL Server 2016. If you act now, you can save $200 on your registration by using the exclusive discount code 24HOP200. That's 24HOP200 until Sunday, September the 18th. To find out more information, please visit www.pastsummit.com. So, I'd like to introduce today's presenter, Kathy Kellenberger, teacher, author, and consultant. Kathy is also the author of Beginning T-SQL, Expert T-SQL Window Functions, as well as Beginning SSRS, which is coming soon.
Thank you so much, Jonathan. As the title says, this is indexing for beginners. I won't be talking about any advanced or newer type of indexes such as column store indexes or the indexes on memory optimized table. This is going to be about the basics. I'm a consultant and I talk to lots of customers who have issues with SQL Server. They tell me their applications are slow. They see timeouts, they don't know what's wrong, and maybe SQL Server used to be fast and now it's slow. Often they have indexes in place, sometimes dozens of indexes per table. They don't really have a strategy, they just kind of add them randomly. So they don't know if those indexes are the right one. So in this session, we're going to learn a little bit about how SQL Server uses indexes to help you get the data back that you need to get, and maybe understand a little bit under the covers about how they work. My customers have tried a lot of things to solve their problems. I often see that they've added processors to the SQL Server, added more cores. I've even seen an instance that had more processors than RAM on the box, which is really, really out of balance. I've seen SQL servers where the hosting company has upgraded to the storage to like world-class storage when really their problem is due to inadequate indexing. Like I said, I've seen customers whose databases have random indexes added. often dozens of indexes on a table with all kinds of duplicates. You may be wondering, well, why is that a bad thing? Well, those indexes have to be maintained every time you do an insert, an update, or a delete. So that slows down. Having too many indexes can slow down your application as well as not having enough or the right ones. The thing that indexes help SQL Server do is work less hard. Imagine that the data that you need is in a relatively large table, and your query is making SQL Server scan or read that entire table. Here's another thing you may not know if you're a beginner. SQL Server cannot actually read the data and work with the data unless it's in memory. So as you know, the data files live on disk, and even though we have a lot of really fast storage nowadays, it's still some effort to get that data off of disk, or actually not really off of disk, but copied to the memory. So the idea behind indexes is that we can have SQL Server work with a much smaller object. Even if SQL Server has to scan or read that entire index, it's doing a lot less work. So if SQL Server can do a lot less work today, as your workload increases, it will have the reserved capacity to do even more. That's called scaling. Scalability is really important. I want to show you a little simulation I call Find My Number Game. It just is a little demo of how an index might work. I'm trying to find my mouse here so I can switch. There we go. So I have a table. I'm going to call it heap, and I'm going to define that word in just a couple of minutes. But this table has no indexes on it, and it's actually all the numbers between 1 and 1,000 in a random order. They're inserted in a random order. So my script, and don't worry about the code here, this is just a simulation, my script will choose a random number and then search through the table and try to find the number. Let me go ahead and run this. And the number I was looking for was 787, and my script found the number in 718 guesses. Let me run that again. Those numbers were pretty close together. This time 741, 831, let me try it one more time, 540 and 445. So every time it had to look through that table quite a bit. Now in real life, a non-indexed table, you'd have to actually look through the entire table because maybe that value you're looking for is in there twice. In this case, I know that the table is unique just because that's how I loaded it. So the other example is finding a number in an index. Again, this is a simulation, and this time I'm going to look for a number between 1 and 10,000 and see how long it takes. So this is not a real index. This is, again, just a simulation. So this time I'm looking for the number 7,184, and wow, that's crazy. It found the number in 12 guesses. Maybe that is just, a fluke. Maybe we won't get that again. Let's try it again. Wow, 9,097. I found it in 13 guesses. What if we increase this number? Let me add a couple of zeros here and make this 1,000,000 and run it again. So this time the number is 695,000 and some change, and the number was found in 20 guesses, 18 guesses. So with an index, it's easy to find exactly what you're looking for because the data is in order. And again, this is just a simulation to show how it's easy to find the data. And this is a binary search that I'm using. So this means that the number of guesses, if I'm remembering my math right, it's the log of base 10. So log of 1,000,000 to the base 10 is 20. So every time I run this, it should be about 20. Let's go back over to the slides. I know that my title says that we're going to talk about indexes, but I really need to back up a bit and talk about tables, there are two types of tables. This is, again, the traditional tables. I know there's some newer types of tables out there. We're not going to talk about those. These are just the basic traditional tables that we've had forever. And one type of table is called a heap. That word may ring a bell because I just showed you a demonstration about how it takes a long time to search through a heap. I like to compare I don't know if these are metaphors or analogies, I never remember the right word, but I like to compare these concepts to real-life objects. So a heap is kind of like a fiction novel. So if I have a novel, it has a lot of words in there, but those words are not in any kind of order as far as indexing is concerned. If the words in that novel, that fiction book, were in alphabetical order, that book would be pretty worthless. It really wouldn't mean anything. This is the right structure for a novel. And in real life, sometimes it makes sense to have the data in what's called a heap, an unstructured table. The other type of table is called a clustered index. This may sound crazy if it's the first time you're hearing it, but the clustered index is actually the table. The table is the clustered index. It's one and the same. So if I have a table, it may start out as a heap. You'll hear people say, I'm going to add a clustered index to this table. But what they're really doing is turning the table into a clustered index. In real life, a clustered index is like a dictionary. The words in the dictionary are in alphabetical order, and you can find them very quickly. Inside that, so if I'm looking for the word dictionary, I know to start at the beginning. I know to start in the D's, and I can quickly find the word I'm looking for. The word is actually what's called the cluster key in this case. The word is the cluster key. There's some other pieces of information in this dictionary. There's a pronunciation, there's an origin, and there's some definitions. So there's more in there than just the key. Let's go back over to Management Studio and we'll take a look at some tables. I'm using the AdventureWorks database, and for those of you who know, Microsoft has given us a new sample database called, I believe it's Wide World Importers. I haven't converted over to that yet. So these examples are going to be in AdventureWorks, which you can download from codeplex.com. I also made a modification to this database. A friend of mine named Adam Mechanic, super smart guy, has a script you can download to create some bigger tables. The tables in AdventureWorks are pretty small, so it's hard to tell a difference sometimes in performance because those tables are small. And then here's one of those tables from Adam's script. Plus, I also created another copy of it without any indexes. So let's take a look over in Object Explorer. If I look at Big Product 2 and expand the indexes, I see there are no indexes at all. So that tells me right away that this table is a heap. There is no clustered index. If I look at Big Product and expand indexes, I see that there is an index there, and it has in parentheses the word cluster. This means that it's a clustered index, and it also is this table has a primary key on it, and if you add a primary key to a table that doesn't have a clustered index, by default SQL Server will make a clustered index based on that key. So most of the time, the cluster key and the primary key are the same. They don't have to be, but most of the time they are. So let me go ahead and show you. I'm going to turn on what's called an execution plan. If you haven't seen an execution plan before, what it does is shows you how SQL Server is processing the query. So even if you have not seen this before, you will get some info. Let me run one at a time so we can pay attention to how long it takes to run. Even if you have not seen execution plans before, you'll learn a little bit about those tonight as well. So I run this query, and it took about a second to run. And if I look at the execution plan, it tells me the data path, where I actually got this data. And it tells me that SQL did a table scan. A table, in this case, is a heap. So if you see table scan, that means it scanned a heap. And the table was big product 2. So that makes sense. If we do the same thing on big product, and this is the one that I got directly from Adam's script, and he did have some indexes in that script. So if I run that, it still took about a minute to run, but a lot of that time is just populating this grid, unfortunately. And if I take a look at the execution plan, I see something very different. In this case, it says clustered index scan. So if you see that, you know that the table is a clustered index. So if you are looking at a heap, it'll say table. If you are looking at a clustered index, it will say clustered index. Now in a little bit, I'm going to talk to you about another type of index that will show up differently here, but we're not quite there yet. So let me switch back over to the slides. I have a lot of example graphics here. Let me warn you, they are extremely simplistic. I'm really not talking about internals or how things are accurately live in the real world. I just want to illustrate some concepts. So these are very, very simplistic examples. So when you have a heap, the data is not organized, but it's inserted in the order, or it's lined up with pointers in the order that it's been inserted. If I want to search in this heap for the letter A, I have to look at each item until I get to the letter A, and I have to continue searching because the A might be there more than once. Here is a very extremely simplistic illustration of a clustered index. It's called a B-tree structure. Now I've represented it here kind of like a binary tree, but in real life it's called what's called a balanced tree. In real life there will be a lot more branches coming out than just 2 like I have here. But I just want to keep this simple just to illustrate a concept. So if I want to search for A in this clustered index, I start at the middle of it, which is the root. So that M is considered the root. What I'm searching for is less than or greater than where I am. So I'm going to head down the left, and there I found my item. Again, I just illustrated a binary search. It's more complex whenever we're talking about a real index under the cover. But I just wanted to illustrate the concept here. So here is a little bit more detail about what's going on. The index can be divided into 2 parts. The top is called the non-leaf level, and that M is called the root. So if you think of it, it's an upside down tree. Normally a tree, the root's at the bottom and the leaves are at the top. With an index, the way we represent it, it's upside down. In those non-leaf levels, that's where the key is stored. If this was a dictionary, we would just store the words in this key. The bottom of the index, the leaf level, contains the key again, whatever column you have chose to be the cluster key. It also contains all the other columns in that table. So in our dictionary example, the leaf level will contain the word plus the pronunciation and the definitions and whatever else might be there. Let's go ahead and take a look at some clustered indexes. We're going to search a table. That's what we're going to do. I've got another couple of troubleshooting tools for query tuning called Statistics.io and Statistics.time. Statistics.io will tell you how many pages SQL Server had to touch in order to run that query. Statistics.time will help tell you how long it takes. Statistics.time is great whenever the query is going to take longer than a second or so to run. It's not as useful less than that. Statistics.io I love. That's one of my favorite tools. Let me go ahead and turn this guy on as well. That's one of my favorite tools because it's very, very consistent between if I run the query and run it again, it won't change, where Statistics.time will often change from one time to the next. I'm going to switch to AdventureWorks. And I'm going to run another command. Don't try this at home, and especially not at work. What this does, remember I talked about how the data has to be in memory for SQL Server to actually return it to you? The buffer cache, this will actually clean that out. It'll knock everything out. So if you did this at work on a production server, it would be like SQL Server restarted. So don't do that. I'm going to do it here just to make sure that I get an accurate Statistics.time on reading, because it will run, if I run a query once and then run it again, it will often run quicker the second time because that data has been cached. So the big transaction history table is another table I got from Adam, and it is actually clustered, and the cluster key is transaction ID. So let's see what happens when I run this one. And I came back very quickly, less than a second. If I look at the messages, I can get more information about what happened. Here's what I focus on. This is the Statistics.io information. If this query had joins, I would see a row here for every table that we touched. And sometimes you'll also see work tables as well. There were 3 logical reads to bring back this data. And the execution time was actually, and I don't use this tool quite as often, but looks like 15 milliseconds CPU time, 2 milliseconds elapsed time. So either way, that's very, very short. CPU time greater than elapsed, sometimes SQL Server throws more than one processor at the problem. I'm not sure if that's what happened here. It doesn't look like it, but regardless, it was very fast. In this case, remember earlier we saw clustered index scan. In this case, you can't see the whole thing, but it's clustered index seek. You can see at the top there. So what that means is instead of reading the entire index, what SQL Server did was able to hop down that balanced tree and find the row it needed very, very quickly. Let's run the other one. So this is a copy of big transaction history without the indexes. So if I run this one, you can see it's already taking longer. So that took 2 seconds to run, where the other one took, under 10 milliseconds. It was very, very quick. If I look here, I can see that logical reads, 143,000 logical reads. That's how many pages SQL Server had to touch in order to run this query. That actually is the same number of pages as if we just did select star from big transaction history without a where clause. In both cases, SQL Server would have to read that entire table. And we can see that it took a little over 2 seconds. If I look at the execution plan, you can see I've got a table scan. In this case, SQL did throw some extra processors at it. That's called parallelism, something way out of scope for what we're talking about tonight. And it also suggested an index that might be beneficial. I'm going to talk a little bit more about that later in this session, but what I have seen a few of my customers do is every single time they got a suggestion like this, they would create the index. And without researching what was there, without really paying attention whether an index was already there that was very close. So that's where they get into trouble, by just blindly following this information. You can follow the information, but make sure you do a little research first. Let's go back to the slides. Remember, there are two types of tables. There are also two types of indexes. Clustered index. We've been talking about a clustered index. Clustered index is the actual table. There is another type of index called a non-clustered index. Continuing along with our book analogy, this picture on the right, hopefully many of you recognize it. It's a card catalog from the library. When I was a kid, I would love to look through this card catalog. I feel like I was a data person from the time I was very young, but now you don't see these very often. If you like to watch The Big Bang Theory, there's actually a card catalog on their set. So check that out if you're a fan of that show. So the card catalog had several indexes. For example, if you have the fiction books, there would be an index on the book title. There would be an index on the author name plus book title. So if you had, let's say, the book title, you could find it. It would tell you the author name and tell you where to find that book. For nonfiction books, it would tell you where to find it according to the Dewey Decimal System. Either way, there was a lot of information in this index. For example, I could find out how many books by a particular author were there by counting the cards. I could find out the published date, the publisher. I could find a little bit about what the book was about. I think there was usually a paragraph or maybe a couple sentences telling me what the book was about. So I could get a lot of information from this card catalog without making a trip to the shelf to pull the book. Eventually, I'm going to want some information that's not in the index. For example, maybe I want to read the book, or maybe there's a specific question that I have, and I'll have to go get the book. One more type of real-life object that applies here is a non-fiction book or a textbook or a technical book that has an index in the back. The book itself is a heap. So the part that you read is a heap. There's a non-clustered index in the back of the book. You can look for a term. So let's say you were reading my T-SQL window function book and you wanted to find out about lag. You could find lag in the index and it would tell you which page to go to. I love that analogy because SQL Server stores the data, the rows on pages, and if I have an index in the back of the book, it also tells me which page to go to. So I really like that one. Either way, it's either we're talking about the card catalog or the index in the back of the book, it's a separate structure. So for example, let's say that there was a term that I wasn't quite sure of, but I knew that I would know it if I saw it, I would recognize it. I could easily read through the entire index in the back of the book and probably wouldn't take me too long. If I wanted to find that term in the rest of the book, I would have to read the entire thing, and it might take longer than I'd want to spend. So either way, SQL Server will do the same thing. If it has to, it will read the entire index. If that's not going to work, if it can't do a seek, if it can't read the entire index, it might go to the table, depending on the situation. And we'll talk more about that in just a bit. Well, let's take a look at some indexes. So there is a command, so you may be wondering, how do I know what indexes are on a table? So let me just grab one of the original AdventureWorks tables, production product, and under production product there are several indexes. There's a clustered index and 3 non-clustered indexes. So if I double click on one of these, I can see what that index has in it. So in this case, it has the key, the index key is the name, so that's what would go in the non-leaf level, the top of the index. And I could also, if I wanted, have what's called included columns. So included columns are kind of like extra bonus pieces of information. For example, in that card catalog, the index key is, let's say, the book title. The included column could be the year it was published. So we are able to do that. So this particular index, it's only on the name, nothing else in it. There is a command called sphelp index that you can use to see the indexes if you don't want to look at that dialog box. So it tells me the name of each index. It tells me the description. Is it clustered or non-clustered? Is it a unique index? So these are all unique indexes. Is it, well, it's located on primary, that's the file group. Don't worry about that for this, kind of above what we're talking about today. And also shows you the index keys. So if there are multiple indexes, or multiple keys in the index, they'll be listed here. One thing this sphelp index does not show you is the included columns. If you download the code sample later from the past 24 hours of past site, I do have a script in there that scripts everything out, including the include columns, so you can take a look at that at your leisure. So let's take a look at this. We saw that there is a, let's see, product ID is the clustered index. So, oh, I'm looking at the wrong table. Big transaction history. So big transaction history, again, one of Adam's mechanics tables, has a non-clustered index on product ID. So if I turn that on and click execute, it runs very quickly. And the execution plan says index seek. Index seek. So that means it was very quickly able to look down the index and find the row that it was wanted. If I change to big transaction history 2, the non-index table, and there are no non-clustered indexes on it either, it takes a second to run instead of immediately, and you can see that it's a table scan, and again we get that missing index hint. So either way, let's see, that was product ID, that guy doesn't have any. Okay, so basically in a perfect world, we'll see execution plans, at least for simple queries, that look like this. There's one other thing, another wrench we can throw in this that I'll talk about in just a minute. But normally an index seek is very nice to see. Let's go back over to the slides. So here's the structure, or the very extremely simplistic structure of a non-clustered index. It looks just about like a clustered index. The top of it contains the key. So in the case of my card catalog, it will contain the title of the book. And again, that's called the non-leaf levels. The leaf level contains the key again. It also has a pointer to the table that it's indexing. So a pointer to the table. I'll tell you how that works in just a second. And also any included columns. So in my card catalog example, that leaf level contains the title. It tells me where to find the book. And it also has the publish date and the publisher. Those are included columns. Those are extra pieces of information that are not really indexed, but they are part of the index, so your query can use them. So what's that pointer to the table row? If the index is pointing to a clustered index, then it will contain the cluster key. What this means is that every non-clustered index pointing to a clustered index, that's hard to say, repeats the cluster key. So you can actually take advantage of that in your query. There's another thing to keep in mind here. You want to make sure that your cluster key is not extremely wide. As a best practice, we want to keep our cluster keys relatively narrow because that cluster key gets repeated in every non-clustered index. So it's going to take up a lot of space. If the table is a heap, then there's a thing called a row identifier that tells you the row. This is a number that you're not going to care about. You're never going to see it in any queries, but it does basically link the non-clustered index to the correct row in the heap. And it's just something SQL Server does under the covers just to make things work. Let's go ahead and go back to Management Studio. Let's take a look at using some indexes. So we are going to turn the execution plan on, and we're going to turn on Statistics.io. We're going to use the production product table just to see what happens when we write these different queries. So hopefully you can remember what will happen if we run this query. We will scan the entire table, a clustered index scan. No where clause. This is really the only way SQL Server can do this. Product ID is the primary key, and it's also the cluster key. So if I'm looking for a specific row, SQL Server can do a clustered index seek. You can very quickly find the row that I'm looking for. When we were looking at the indexes earlier, we saw that there was a non-clustered index on the name column. So if we go back over here, this is the one we looked at. There's a non-clustered index on the name column. So if I am searching for a particular name and I don't have any other columns selected, I get an index seek. Again, this is what I hope to see in a perfect world. Another wrench will be thrown in just a minute. Here's another query. I do not have any index on color. So hopefully you can figure out what the execution plan is going to look like here. If I look at the execution plan, I see a clustered index scan. This query and also the very first one I ran have to do the same amount of work. And actually, I haven't been looking at the logical reads. It's a really small table, 15 logical reads. But if I run this guy again and look at the logical reads, again 15. So this particular table is really small. It only has 15 pages. So if I'm able to use, in this example, I'm able to use that non-clustered index to get everything that I need for the query. So if I run this one again and take a look at the logical reads, only 2. So it's much more efficient if I can do that. Let's go back to the slides. Another thing to keep in mind is the column order of your non-clustered indexes. It's really, really important. A phone book is not a non-clustered index. It's actually a clustered index, but I can illustrate the point with a phone book. So a phone book is organized by last name and first name, and inside there we'll find the address, we'll find the phone number. Imagine that you met someone at a party or whatever, and you cannot remember their last name, but you had a phone book for the town where they lived. If all you had was the first name, how would you locate that person? You would have to read through every single page of the phone book. You probably wouldn't get too far before you would get bored. Luckily, SQL Server is a computer program. It does not get bored like people do. So the column order is really, really important. So let's say we had a non-clustered index, and we knew that we were almost always going to be searching on last name. We would probably make that the first index or the leading, the first key or the leading key in that index. If we search on city sometimes without last name, maybe we might want to create another index that leads with city. So the column order is really, really important for your queries. And again, I don't want to suggest that you go out and create an index for every query that you write. That's really impossible. But what you'll do is pay attention to your workload and figure out which queries need tuned and go from there. So let's take a look at how indexes, the order of the indexes are really important. So let's go ahead and turn this guy on again, and we're looking at person-person. So person-person has 3 indexes. One is the primary key clustered index. This is the one I'm interested in. Last name, first name, middle name. So here's a query where I am searching on last name. If I look at the messages, I can see that there are 3 logical reads. SQL Server looked at 3 pages to solve this query. If I look at the execution plan, I see an index seek. So that's pretty nice. Let's take a look at this one. This one searches on first name. If I look at the messages, I see that it took 109 logical reads. That's quite a bit more. When I searched on last name, it was only 3. If I look at the execution plan, I can see that it did use my non-clustered index, but it had to scan it. So since it didn't have last name, it had to just look through every single, entity or every single key in the index until it found the first name it was looking for. It had to bypass last name. Here's another interesting thing you can do with execution plans. I'm going to run these 2 queries together and take a look at the execution plan. So one thing you can see is a relative query cost. The overall batch has to add up to 100. So this tells me that 3% of the effort was taken when it was SQL Server was able to use the non-clustered index as a seek, and 97% of the cost was taken by scanning the index that I had to do when I searched on first name. So this is another really cool aspect of execution plans. The thing with execution plans, they don't tell you the truth 100% of the time, so make sure that you combine execution plans, statistics.io, and statistics time to really understand what's going on and how to troubleshoot your query. Let's go back to the slides. There's one more concept I'd like to cover, and this is covering indexes. Pardon the pun. I kind of don't like this term covering indexes. I love covering indexes, but I don't like the term per se because it sounds to me like it's a property that I can turn on and off. What covering index really means is that for a specific query, I have an index that has everything in it that I need to solve that query. For another query, that same index is not covering. So it really describes a situation more than the property of an index. For example, in my book analogy, well, my library analogy, I can find out the published date by looking at the card catalog. But if I want to find out the first paragraph on page 47, I'm going to have to go and look at the book and turn to page 47. So if I'm looking just for the publisher, that's covering. If I'm looking for that first paragraph on page 47, that's non-covering. The same index, just 2 different queries. I've got one more demo for you. In this one, I am going to create a copy of a table so I can add some indexes without causing any problems. Let's turn the execution plan on. So this table is a copy of the regular sales order detail. I have added a primary key, sales order ID plus sales order detail ID. Remember, if I just add a primary key without specifying that I don't want it to be clustered, SQL Server will automatically create a clustered index. So right now I have a clustered index on this new table that I've created. Let's see, I've got statistics IO, and I turn that on. And right now, all I have is my clustered index, no non-clustered indexes. If I take a look at that, you can see I did a clustered index scan because there's no index on product ID. So maybe I want to look at product ID frequently. I'm frequently querying that for product ID. So let me create a non-clustered index, and let's run this query again. This time, I got an index seek. And even though I only specified product ID for my index, because the cluster key involves these two columns, those are automatically part of my non-clustered index. So I get this guy for free. I get sales order ID for free. What happens if I add another column that's not part of my index? In this case, I get what's called a key lookup. These are generally bad news. Notice again, inside my query, inside my execution plan, everything's got to add up to 100. In this case, SQL Server is telling me that it took 99% of the effort just to go out to the table and find the order quantity. So these can be bad news. That's that wrench I was talking about. So how do I solve this problem? What I can do is, instead of adding another index, I'm going to drop this one, and I'm going to recreate the index with an include column, order quantity as an include column. These are those extra pieces of information. I'll run that query again. Is that the same? It's actually a little bit different. I'll just come back and run this one. Run that one again, and now I have an index seek. So that is fantastic. I really, really hate seeing key lookups. I hate seeing them almost as much as I hate seeing clustered index scans. All right. So in summary, I want you to remember that a table is a heap or a clustered index. It's one or the other. A non-clustered index is a separate, smaller structure, and the non-clustered index points to the table. The key defines the order or the structure of the index, and with non-clustered indexes, we can also add included columns. So, Jonathan, are there any questions?
Hi, Kathy. We have 3 questions.
Okay.
So, first off, we'll start with Adam's question. Adam asks, are there pros and cons for using multiple index keys versus included columns?
Yes. So let's say your where clause contains multiple columns in it. You might get better performance by adding all, let's say there's 3 columns in your where clause. You might get better performance by adding all 3 of those to the index key.
Okay, and for the next question comes from David. David asks, if the non-clustered index links to the primary key column, when it is the clustered index, would there ever be a case for including said key column as a covering index column on the non-clustered index, or would that just be redundant?
You don't have to do, so I think what you're saying is, should I add the cluster key as an included column? I wouldn't do it. I'm not really sure if SQL Server repeats it there. I mean, I guess you could go ahead. I see it done a lot, but you don't have to. I guess if you add it there, then it's going to remind you that it's there, and I really would doubt that SQL Server is going to store it twice. Never checked into that. That's a great question. But generally, I leave it out.
And Kian, well, we have more questions coming in too.
Okay.
Kian asks, any use case for using heaps? Sorry, I just scrolled up. Any use case for using heaps or non-clustered indexes over clustered indexes?
Okay, so non-clustered indexes and clustered indexes can be used together. As far as heaps, so one of the main use cases for heaps is staging databases. So for example, let's say you've got a big data warehouse and you're pulling data in from all different sources in your environment and you have a staging database. Sometimes they will keep those as heaps just because they'll load faster. So if you're loading a large amount of data into a table, you might want to go ahead and just keep it a heap. That's the first thing that comes to mind to me.
Okay, the next question is from Lori. Lori asks, is a unique clustered index the best?
Yeah, so I didn't really go into too much on best practices. It is the best. A unique clustered index is a good practice. I didn't talk at all about fragmentation because you can only talk about so much in an hour. But if you have a clustered, so actually unique, not non-changing. So a really good, nice practices for clustered index is unique, non-changing, and narrow. So it really depends on the situation as far as unique. Most of the time they will be unique, and I think it probably helps the performance. But I think I'm getting myself down a rat hole here. But you know, sometimes when I have processes that I create temp tables for, I often create a cluster index on how I'm going to be joining later, not on what's unique. So it just depends on the situation. But I'd say most of the time, yes.
Okay, and the next question is from Ricardo. Ricardo asks, does SQL Server add a uniqueifier to non-clustered indexes or just to clustered indexes?
Right. So if you have a clustered index and the key is not unique, it adds a uniqueifier because it's pointing to the row. I have not heard it add to a non-clustered index, so I'm going to have to say I'm not sure, but I think no. I think no on the non-clustered index. I think it's just the clustered. And that way you can find the row. That way there's a unique identifier for each row of a clustered index if the cluster key is not unique. Something I really didn't talk about.
Okay, and the next one is not a question. It's more of a thank. Lee just wanted to say thank you so much and great analogies and explanations. The next question is from Gotham. Does the covering index take storage space?
Absolutely. All of the indexes take storage space. Another reason why we don't want to make them too gigantic. We want to keep them as small as possible and still do the job. But yeah, they definitely, and again, covering is not a particular type of index. Covering index means it has everything it needs for that specific query. Another query, it won't be covering.
And the next question is from Kamir. Kamir asks, is there a way to monitor performance for any previously set index without doing an execution plan for each query?
Repeat that, please.
Is there a way to monitor performance for any previously set indexes without doing an execution plan for each query?
Previously set indexes. I'm not quite sure I understand the query, or query.
Yeah, I'm looking at it. I'm guessing they're asking, is there a way to monitor performance for any previously created indexes without doing an execution plan for each query?
I mean, you can query the cache to see what's been run recently, to look at performance. And SQL Server 2016 has this new thing called a query store where you can look at what's happened in the past. I'm not really quite sure I understand the question.
Okay. The next question is from Mike. Mike asks, can you define sargeable and non-sargeable?
fantastic question that I didn't cover at all. So sargeable, it stands for search argument. Sargeable means that SQL Server was able to utilize that index as a seek and didn't have to scan it. So for example, let's say I have my last name and I know that it has the letter MITH, but I don't know the first letter. SQL Server, when I do a %sign MITH, that's a non-sargeable. SQL Server will not be able to seek. SQL Server will have to scan. There's a lot of things that can cause a predicate to not be sargeable, such as applying a function to a column. But that's a great question. Again, more than we can cover in 1 hour.
The next question is from Dong. Dong asks, Mike says thank you. The next question is from Dong. Dong asks, for ETL process, is it standard practice to drop the index first before running it in ETL and then rebuild the index?
That is a very common practice. Definitely a very common practice. And that's similar to that other question about using heaps. Sometimes they they don't bother with a clustered index at all. They just use the non-clustered. Or sometimes they just load really fast and apply the indexes later. So that is a very common practice.
And the next question is from another Mike. Mike asks, what is the maximum number of non-clustered indexes on a table?
You can have 999. That's a lot.
Yeah, that is a lot.
There are situations where you could make sense to have a lot like that, but we didn't.
What's the most you've ever seen?
On a table? I don't really, there's this one customer I had that had a couple dozen on every table. So there's certain use cases for having those large amounts. There's a thing called a filtered index. So let's say you have a column that's mostly filled with null. You could have an index and add a where clause to it, where column A is not null. And then you could have, let's say you had 20 columns that were mostly null. You could have a filtered index on each one of those. So that's why they have so many. It's because of the filtered indexes.
Okay, and that appears to be the last question there.
Okay,
so
fantastic.
Let's see, moving to the next slide here.
Oh, sorry.
That's okay. So make sure you guys stay tuned for our next session. It's a 500 level guide to career internals with Brent Ozar. So make sure you tune in for that next, because it's guaranteed to continue the excellence of 24 hours of pass. And thank you for attending. And you guys and everybody have a great day.
Thank you very much, Jonathan.
Thank you.